Okay, so welcome everyone to today's 1W-MINDS seminar. So today it's my great pleasure to have Professor Bing Dong to speak in our seminar. Professor Dong is currently Associate Professor at the Beijing International Center for Mathematical Research, Peking University. Bing's research focuses on mathematical modeling and computations in imaging and data analysis. A special feature of his research is blending branches in mathematics and machine learning, which include bringing wavelet frame theory, variational techniques, and nonlinear PDEs, bridging differential equations and optimal control with deep learning. So he's currently serving on editorial boards of several journals, including Journal of Computational Mathematics, CSIM, Transaction Applied Mathematics, and also he has received several awards. In particular, Bing is invited to give a 45 minutes talk at the International Congress of Mathematicians this year. So today he will talk about learning to solve parametric PDEs. Bing, the stage is now yours. Thank you very much.
All right, thanks for the invitation and thanks for the introduction. Today I will talk about how can we use machine learning to help us solve parametric PDEs. Well, actually I didn't pack a lot of stuff today, so hopefully we can have well, if you have questions, I think you could. Well, I don't know if you can unmute yourself, but I hope that this talk can be interactive, or you can just leave a message and maybe I can just pause and look for questions. Okay, so this is today's plan. I will give a relative brief overview and the motivations on the impact of deep learning and in particular the impact of deep learning or machine learning in scientific computing. And in assisting scientific discovery, and then how we view deep learning with optimal control, and why I think that this is a good perspective. And then after that, I will specifically talk about solving certain type of parametric PDEs. Well, parametric PDEs is a big class, but I will focus on certain type of parametric PDEs. In particular, I'm gonna talk about electromagnetic simulations. This is a joint work with 1W-MINDS for their MINDS team, specific working on AI plus scientific computing. Okay. We know that this is what I pulled out from Wikipedia, where the deep learning revolution started around 2012 from the field of biomedicine and computer vision, and since then its impact has spread to many fields in natural sciences, social sciences, and engineering. And even beyond that. But in this talk, this falls into the category of what we now call it, machine learning plus scientific computing, or some people call it scientific machine learning. Okay. So before I proceed, I think at least this is my personal experience that if you want to find a good combination between machine learning techniques with scientific computing, because scientific computing is a very rich and mature field, and it has been developing for many years. So if you want to incorporate a new technique into something that has such a rich background, you need to know very well what's the pros and cons of this new technique. Well, deep learning is what I mean by new technique. So what makes deep learning that are particularly successful nowadays? Well, in my own opinion, is because well, basically three aspects of it that makes it quite successful. The first one is it is able to approximate a very complex mapping, in particular high-dimensional nonlinear mappings. Okay, this is what deep neural networks or what a composite answers that is particularly good at. The second is that it can also make very fast inference. Okay, it approximates a very complex mapping, but after you have approximated this mapping, after you have trained your deep neural nets, for example, and it can make very fast inferences. Okay, and also the accuracy. It's not high accuracy. It's not just 10 to the -8, 9, 10 accuracy. It's about right accuracy. The reason that I said it's about right accuracy is because this accuracy is actually task driven. When you train this network, or when you train your model, it's typically in an end-to-end fashion where you have your specific task, in hand, and based on this task, you create a loss function, and then you train your network, by minimizing that loss function. So, so your network, when you approximate a complex mapping, this end-to-end training enabled you to train a network that generates accuracy that is accurate enough to solve the task that you're interested in. I think these are very important ingredients. Okay, approximating high-dimensional nonlinear maps and can make fast inference, and the accuracy is not super accuracy. It's task-driven and it's about right accuracy. Okay, so with this, I think perhaps the most exciting development in deep learning or machine learning is the AI-assisted innovation. So it's AI-assisted innovation. It's not AI innovation. Well, here AI, I mostly mean by machine learning assisted innovation. Well, this is there are many examples. I'm going to dive into examples a little bit later, but I think the success mainly oriented around the strength of deep learning and avoiding the weakness of deep learning at the same time. Okay, so there are successful examples that most of you may already know in biology, chemistry, and material science that's harmful to deep potential, and also in antibiotics discovery. And this is a paper. It's in 2012 in Cell, and it's actually a cover page paper. And also in physics, that we see that people use machine learning to do system identification and to do fast simulations, and use them to do quantum design, and also use them to control in control tasks as well. Okay, so there are many other examples as well. So all of these are actually taking full advantage of what I just described, the three important aspects of deep learning that makes it very effective in assist us in doing scientific discoveries. And other than science, mathematics as well. I think this is a work that I like a lot. This is work jointly with several pure mathematicians and with DeepMind. And DeepMind helped them develop machine learning tools to help them to generate intuitions, by quickly going through tons of data and finding potential patterns, and these potential patterns can inspire mathematicians to create conjectures and then later improve the conjectures. So this is how machine learning can assist in innovations, not only in science, also in mathematics. And there are other examples in engineering as well, not just math and science, engineering as well. Okay. So given these successes, there are still a lot of challenges in deep learning, and you may know very well some of them. So I just list the ones that I think are very critical. The first one is generalization, or in the term of numerical analysis, accuracy, right? And we don't quite know, we don't quite understand yet the inner workings of stochastic training. Sometimes just with when you train a very huge network, and you think of it's a lost landscape, there must be a lot of local minimums. But stochastic training, just stochastic gradient descent, for example, it works well in general. But sometimes it doesn't work. Sometimes it works well. So what is the inner workings of stochastic training? How can we actually guarantee a good generalization? Before we do the experiments, we need some. We want some theoretical guidance in designing the network architecture and also the training algorithms. And model robustness, or in the term of numerical analysis, that's stability. Okay, it includes adversarial and also distributional robustness. This is the robustness is very important, because when you train your model in your lab, and after that you release it to the wild, and sometimes the test data that you encounter in practice come from a distribution that is data distribution that is different from the distribution that you use during the training, and this is very often that you encounter in practice. So how can we make sure that the model that we choose, the architect that we choose, the loss function that we choose, and also the training algorithm that we choose, all of them combining together, all of those inductive and implicit bias combined together, we end up with a model that is not only accurate but also robust to distributional shift. Okay, so I think these are the two most important ingredients that we want. And before we can fully solve that, I think this will be the main obstacles in front of deep learning, for it to have an even wider, industrial applications, and also in other fields, as application in other fields as well. And the third one that we hear people talk about a lot, but for me, I'm mostly interested in the extent of interpretability such that it can assist us in scientific discovery. And if you think about interpretability, I think the definition of interpretability is relatively vague. But I think if you think about who that you want your model to be interpretable to, then they may have a different criteria for the interpretability. For example, if you ask a general user whether the user want the tools or the models to be interpretable, I don't think they want interpretability in general, right? Because I use a lot of high technology the devices. I never ask someone to explain the inner workings of the device, because the first two ingredients, they always work and it's very robust. So I think for general users, they don't want interpretability. And for researchers that is outside the machine learning community, well, they don't want interpretability that much. They just want the model, to be interpretable so that it can assist them in scientific discovery. For example, I think if for mathematicians, they don't really want, they don't actually need the model to generate a very logical, flow of thoughts to help them thinking, because they do that very well. Okay, they just want the machine learning to do what they're good at. What they're actually good at is fitting complex mappings and do very fast inference. And this can help mathematicians to narrow down in a very short time a lot of possible possibilities and to generate intuition. So I think for people working in science or math, they want a relatively weak interpretability. I think the very strong version of interpretability is actually for people working in machine learning community. They want to know how to make sure that the model generates well, the model robust, what is actually the workings of the training algorithms, or how should we choose the loss function, and etc. And so far we have a relatively weak understanding of deep learning in general. Okay, so perhaps I think a promising approach to to alleviate the pending issues, but not may not from a theoretical point of view, but at least from the computation and modeling point of view, is by combining handcrafting that we actually are very familiar with in the community of scientific computing with learning or with data-driven models. Okay, so that we can take advantage of the traditional models that are actually relatively accurate and robust and have perfect interpretability, but may not be accurate, may not be adaptive enough to certain given situations, and that's where data-driven approach can help the handcraft models that we use a lot in scientific computing. Okay, so how do we actually combine the ideas? I think optimal control gives us a very convenient framework. Okay, so let me just explain this idea a tiny little bit, and later on I'm going to show you one example where we actually take advantage of the sort of philosophy that I just described, and that would be a more concrete example. Okay, so just think of training a deep neural networks, and because of the deep, so it's actually a composite structure, and if it's a composite structure, you can actually write it into this iterative procedure, and well, at least approximately, okay, because here I assume that the dimension of x is not changing, so it's an approximate version of it. And this k indicates the layers, and u is the in the terms of optimal control, it's the control parameters, but in terms of deep neural networks, those are the parameters of the deep neural network that need to be trained. The first term in the loss function J, that's the terminal loss, and the second term is the running cost. Okay, and W is the model noise that you may have, and this this structure describes supervised learning and also method learning can be written in this form as well, and also model-based reinforced learning can also be written into this form by slight modifications actually. So if you want to combine handcraft and data-driven models, what you need to do is you need to first of all, the traditional algorithms that you have for solving a given scientific computing task, it can often be written into this iterative procedure, and some component of it may be hard to handcraft. Okay, if you work in scientific computing, then you must have quite a few examples of such algorithms where you have some component, you have to design it in an ad hoc fashion, and now actually you can make those components learnable, okay, and create your control parameters. And then if you have you have a training data and you have ground truth or approximate ground truth, you can do supervised learning, and if you don't, you can do unsupervised learning, and that's just the designing property of your objective function, and you can do BP training, and in the end you're going to have a combined model that is combined with your handcraft and data-driven models. Okay, so this is a very general idea, the very general concept, and actually this actually help us to combine modeling, traditional modeling and the data-driven model. Okay, and in a relatively more systematic. Okay, now so let me dive a little bit into the topic that I'm going to talk about today, that is learning to solve PDEs, in particular parametric PDEs. Let me just give you a very brief review of how people trying to use neural networks to solve PDEs. Well, this is a highly incomplete list, and actually some of the, well, I classify them into two categories, but some of the work cannot be classified into this category. So this is not by no means complete. Okay, but this summarize a good portion of it. So first of all, I think that I classify it in terms of which object that you want to approximate using your neural networks. The first category is that you want to use neural network to approximate the solution. Okay, and I think this is the most natural option, because we do this in traditional numerical PDEs, right? We choose polynomials, we choose finite elements, we choose Fourier basis to as an answer to approximate the U, and then we plug it into our differential equation, and then we derive an equation for the coefficients, and then we solve that system, linear or nonlinear system. Okay, that's the the traditional numerical PDE approach. And now we have deep neural networks. They have their advantages, especially approximating high dimensional functions. So then we can just use deep neural networks as the new answers to approximate your solution U. Okay, and this L is it's a general notation for your differential equations, linear or nonlinear, and it includes possible initial boundary conditions in this. So this is just a little bit sloppy notation, but it shows the the main ideas of this approach. Okay, so after you have plug it in, then you can just simply minimize the square laws of it. Okay, or you can minimize if there's a variational principle behind it. Okay, for example, if your PDE is a Euler-Lagrange equation of a given energy functional, then you can try to minimize that energy functional, or maybe some other options that you have as well. But for most of this, for all these approaches, the idea is to use neural network to approximate the function U. And this is particularly effective if your solution U is really in high dimension. This is the work done by Rina and Bing, who was who's Rina's PhD student. They call it deep grids. So they just minimize an energy functional, but this U has a variable x that is really high dimensional, dimension 50, 100, or even higher. Okay, and this actually takes the full advantage of the of deep neural networks that is very effective in approximating high dimensional functions. And in low dimension, it may also be effective. For example, if you have a very complex boundaries and the generating meshes for those complex boundaries is very time consuming, especially in 3D. We see this this comes out very often in engineering tasks. For example, you want to do fluid simulations of a combustion engine, and you have very complex geometries, and it takes hours or even days to generate a high quality mesh. And this may also be beneficial because this answers is a mesh free, or you can think it as a adaptive mesh, because it learns during the training it finds a good tessellation of the space and also a good representation at the same time. Okay, so it's a very convenient mesh free approach. So it may also be beneficial if your differential equations has a very crazy boundary conditions, like the example I just gave you, or maybe in Parse Media that you have an example like this as well. Okay, so other than high dimensional, in lower dimension, deep Gaultian method or physics informed neural network spins are some of the earlier works, and also some other works as well, like for example, Zhixin Xu and Wei Cai, they had worked on this multi-scale neural networks, and they show that if your input has if you enforce a multi-scale structure in the network, it can improve the approximation of the network. We also use this in training in solving differential equations that does not have an apparent multi-scale structure. It still helps. I think it helps to make the loss landscape more friendly to to the stochastic training algorithm that we use. I think we use LBFGS and sometimes atoms. Okay, so this is the first approach where we use deep neural networks to approximate solution U, or you can use the deep neural networks to approximate the solution mapping. So what do I mean by solution mapping? Well, so let me just give you this one example. So let's say that you solve a PDE that has that is a parametric PDE. So this eta could be your initial condition, could be your boundary condition, or could be the shape of your boundary, or could be any coefficients that you may have in your differential equations. So you want to find a solver. For example, your traditional, any of your classical solver is a solver for parametric PDEs, right? So just given this eta and this solution mapping that maps your eta, for example, your initial boundary conditions to the solution that you want. Okay, so this is what I mean by solution mapping. Why approximating a solution mapping may be beneficial comparing to approximate solution U? Well, this is because if you're solving a parametric PDEs, and when your eta changes, if you use the first approach, then you need to retrain. You need to do the training from the beginning. Okay, this may be very inconvenient to do. Because for certain tasks, I'll come back to this. I think there are actually a lot of tasks where you need to have a solver that can efficiently generate. It can be trained offline, but when you apply it online, you want it to be very efficient, to apply to a novel instance of this app. Okay, and within this category, there are two subcategories, and I categorize them in terms of how much it actually relies on classical solvers. Okay, and the first category is by integrating machine learning into classical solver. So you start with your PDE solver. You can choose your favorite PDE solver, for example, multigrid. Okay, often this classical solver is an iterative solver, and if you know your solver well, then you would know that there are certain ingredients, certain components. If that's this KJ, this subset of this 1 to k index, that is it's a little bit ad hoc when you actually design this algorithm, or you think that this component should be data adaptive. It should be adaptive to eta. Okay, but you just don't know how to to craft a formula that actually tells you how exactly that you should adapt to eta. And those are the components that machine learning can actually help us. So you can replace those components by neural networks. And this pretty much includes these examples that I show you, including the PDNet that we actually developed in 2018, where we build machine learning ingredients into the finite difference approximations of of the differential equations, and the learning component of it is just the finite difference approximations, the convolution kernels that approximate the finite difference approximations. Those are the learnable ingredients, and also forming the part of the forming of this operator L actually approximated using deep neural networks as well. Okay, and there are many other examples as well. Okay, so another class is what I call direct approach, where it's more like a black box approach, but this could be can be very effective as well. Okay, so the earliest work that I know is done by Kru, Liu, and Ying in 2017, where they try to establish a black box mapping using a convolution network that established a mapping between a term of your differential equations. If I recall correctly, it's a term of a nonlinear shortening equation, and map is directly to the physical quantities of the solution that we're interested in. Okay, so it's a crazy mapping, but it's approximated using a deep convolutional network. Okay, and other examples includes and this is what they call deep ONet, deep operator network. And this is the flow map, and this is the Fourier neural operators, and this is the Galerkin transformation, and all of these are actually trying to establish a mapping that can be written into this form, where it's the it establishes a network that has certain structure, but not as structured as the first subcategory. Okay, so it's closer to a black box, but not entirely a black box. Try to establish direct mapping between the hyperparameters in your PDEs, the initial boundary condition, the shapes, and etc., the coefficients of the differential equations to the solution. Okay, and the advantage of this approach is that once you have trained your network, you don't have to train it again when you see a novel instance at. Okay, you just do a very fast inference. Okay, but the downside of this type of program, at least for the majority of them, is that you need to have a meshing. You need to have a mesh a priori. Okay, you need to generate a high quality mesh, or your solution needs to be defined on the grid. Maybe I think the only exception is DeepNet, but you still need to think about how to properly encode your ADA into this input. Okay, so there are some other works that I didn't include in here, is that you're trying to find a combination between the two, where you don't want to train from scratch. So we're looking at approximating the solution mappings, but at the same time we don't want to do meshing. Okay, it could be very time consuming. So that we want to take a full advantage of this adaptiveness of deep neural networks, and this can be done. And this is one of the work that we did with Huawei, and I'll come back to that in a minute. Okay, so other than the pros and cons comparing this first and two major categories, and what are the pros and cons of this the subcategories in approximating solution mappings? Well, I think for direct approximations, it's very free and very easy to use, and especially when you don't have a very clear principles or equations describing this mapping. Well, in that case, you cannot really rely on a very very reliable PDE solvers. And maybe trying to establish a direct mapping is convenient. It's very convenient to do. It could be very very fast. It has a relatively high accuracy. But comparing to the first subcategory that is integrating with classical solvers, is, well, the downside of it, maybe if you look at longer time predictions, because of this, the direct approximation does not heavily rely on the differential equations that you're solving, then sometimes it's difficult to make accurate long-term predictions. So this is one of the examples that we recently did, comparisons we recently did with with this Huawei's MindSport group generated these comparisons. We just compare the predictions of 2D Burger's equation by training a PDE net and also a foreign neural operator, an FNO. So first of all, FNO has just 3 magnitudes more coefficient than PDE net. And this is, well, actually natural because for the second approach normally you have a lot more trainable parameters than the first than the approach of integrating with classical solvers, and also to train FNO because it has so much more parameters than PDNet. We use 20 more training data, 20 times more training data for FNO compared to PDNets, and this is the prediction. And well, in the light green or light blue strand, this is actually the data that we this is actually the time, the temporal span. I think it's 10 delta t time span that both models have seen during the training, and this is all temporal extrapolation. And if you look at within this temporal band, I think both model does well, and sometimes FNO has its advantage in terms of accuracy. But if you look at the long-term accuracy, FNO doesn't do as well as PDNets. Well, I think that the major reason is because of PDNets actually building mostly upon the different equations, and the model itself helps to suppress the accumulation of prediction errors when you repeatedly apply the learned module during the predictions. Okay, so I think this is the particular advantage for an approach where you integrate machine learning into a classical solver, but you mostly rely on the classical solver. Okay. So this is a overview of how a majority of the machine learning approaches for solving PDEs. So now let me dive into the work that I want to talk about. The first work is a joint work with Qinchao Xu from Penn State University, and also a PhD student that me and Qinchao we co-advised. So this is a little bit recap of what are parametric PDEs, where you have your differential equations depends on a certain hyperparameter, this eta. And in this particular work, we consider a relatively simple version of this eta, where this eta it belongs to a domain that is a subset of a finite dimensional space, but it could be a subset of an infinite dimensional space. In particular, this eta could include the shape of the boundary as well. So I'm going to come back to that in the next part of the work. And so that, well, your solution would depend not only on the spatial and temporal variables, but also depend on your parameter as well. Okay, and here is a very simple example, and this eta will be epsilon and theta as well. This is just an anisotropic diffusion where this theta measures the orientation of the anisotropy, and the epsilon quantifies the significant, the severity of the degree of the anisotropy. Okay. And why should we care about parametric PDEs? Because, well, the parameters actually have very practical meanings. For example, it could mean the shape parameters. For example, you want to do airfoil design so that what you want to optimize eventually is the shape of the wings, and so that you can maximize the profile of your lift and drags. Okay, for example, and it could be also your material parameters. It could be your orientation parameters in flight controls, and also it could be your initial and boundary conditions as well. And so that those scenarios that would require us to develop a solver that is effective not only solving for a certain given eta, but effective in solving for a range of eta, for eta within this this domain D, includes inverse problem, uncertain quantification, design optimization, optimal control, and so on. Okay, so there are a lot of practical scenarios that require us to have an effective solver for solving parametric PDEs. Okay, So in this work jointly with with Yuyan and Jin Chao, we look at a linear problem. We have a linear PDEs and we discretize it, and then we end up with a linear system. And we want to solve this linear system very effectively. And one of the most effective algorithm is a multigrid method. However, if you're solving a differential equations like this, the CPU time of multigrid can go up significantly. When eta is within a certain range. For example, when epsilon for given theta, I think this example is where theta is 0, but epsilon goes very close to 0, and the wall time, the entire computation cost would increase. Okay, so our objective is to start with multigrid and use machine learning to help multigrid to be adaptive to this anisotropy, to this eta, so that we can suppress the increase of computational time as much as possible when epsilon is close to this to this certain range. Okay. So how do we improve multigrid? Well, there are certain ingredients that we can think of improving. The first one is smoother. This actually was the first choice that we thought about, and also prolongation restrictions as well. So in this work, we try to use machine learning to improve the smoother. But the question is, can actually machine learning help, and how should machine learning help in this? Okay, so if you remember the optimal control framework, if you want machine learning to help, you just think you need to try to relate multigrid, this multigrid algorithm, with deep learning models. Okay, when you actually relate them, it will be easier to figure out how do we actually combine it. Okay, so this is the work done by Jin Chao and Jun Cai, who was his PhD student in 2019, where they write the multigrid algorithm in terms of this iterative procedure, and then they make this a convolutional neural networks. So what do we do? Well, this is just a writing of a multigrid algorithm in terms of this iterative algorithm. If you can write it into this iterative algorithm, well, this is it's a dynamic system. Okay, but everything in here at this moment, everything in here is already fixed. There's no control parameters in it, so it's a deterministic system, nothing to be trained. So what they did in this work is that they make the operator, the smoother operator B, okay, this operator A, okay, which comes from the discretization of your linear system. If you use a basis that is shift invariant, it can be written in terms of convolutions as well, and also restrictions and prolongations. They can all either be expressed precisely or approximated by convolutions. This is actually what they did. They take out this, this going back to the, to the finer level, because they're not looking at solving PDEs. They're actually using this architecture for image classification. So they only look at the encoding part of this algorithm and make it convolutional networks. Okay. So in this work, because we're solving PDE, so we're actually using the PDE solver version of the dynamics. So we call this PDE MGNet, okay, which just pretty much the original multigrid written in this dynamic system fashion, and this is just a demonstration of a two-layer two-level multigrid, right? You do a smoother and you calculate this this arrow, and then you just compute the residual and you restrict it to the coarser grid, okay, and then you do the smoother, and then you just prolongate and you update your solution. So this is just a two-level version of it as a demonstration. And if you want to train it, loss could be this unsupervised loss, because you're solving this linear system. Okay, so this is unsupervised learning. Okay, but of course, if you do it this way, then you will be able to solve parametric PDEs, but you need to train a network for each given hyperparameter, right? Because if you train it, if you make it trainable, then it's not obvious how you can actually make make a control parameter just adapt it to this to the hyperparameters that is affected in this operator. Okay, so what we did is we try to make this learning suitable for solving the parametric PDEs. Okay, so actually in machine learning there is a concept called multitask learning, and also meta learning can actually help us to design a solver that's not only for that is not for a specific given ADA, actually for a class, for a set of ADA. Okay, so if you think of learning a solver for a specific given ADA as a single task, then learning a solver for a set of ADA will be a multitask learning. Okay, and this perspective, the benefit of having this perspective is that you'll be able to leverage the common structures hidden in the task, because solving the differential equations for different ADA, they have very common structures that you want to take advantage of. One of the very effective approach in machine learning to solve multitask learning is meta learning. Okay, this includes, for example, MAML, and also hypernetworks is another very popular approach. And in this work, we actually use this hypernetwork because you can also approximate, the first approach using hypernetworks as well. Okay, so we just choose, we just think of, how should we actually design a hypernetwork that can make, this multigrid algorithm adaptive to this hyperparameter data. Okay, so this is, the algorithm that we call meta NGNet. By introducing a hypernetwork, we call it meta NN, that takes the residual R and also the this operator A ADA as the input. Because we're approximating a linear differential equations using a system that is translation invariant, so this A can be represented by convolutions. So what we actually input into this network are the convolutional kernels of this operator A, and also the residual as well. And the output of this hypernetwork are column vectors. And then what we do is we do a subspace correction in the space generated by those spanned by those column vectors. Okay, this column vector doesn't have to be linearly independent. Okay, so this is the design of the meta NN that takes the input of R and A ADA, and then outputs a set of column vectors, and then we do subspace corrections in those space. And this is actually mimicking. It's a certain generalization of Krylov subspaces where we use a fully connected network to generalize polynomials of this operator A, and then we use a DesNet structure to generalize this matrix vector multiplications. Okay, well, at least empirically, using this type of architecture, it works very well. But we didn't actually do a lot of ablation studies on choosing different architectures. Okay, so you can actually train it using this unsupervised loss, and actually because the algorithm mostly rely on the traditional multigrid solver, so you can actually prove convergence for Poisson problems, but we cannot prove that the data-driven method, the meta MGNet, is faster than before the multigrid, but we can only prove convergence. If you want to prove it faster, you have to sort of know you have to solve the training problem of deep learning first before you can actually prove that you will be able to find a particular set of coefficients that does better than than a classical solver. Okay, so it's very hard to prove improvement, but proving for convergence is not that hard actually. So this is a very simple test for the equation that I just showed you with theta within this range and epsilon within this range, and with indistributional test, that is the generalization test that we can have up to 7 times speed up comparing to the multigrid method with Krylov smoother. And also in our paper, we tested, it has a very good, extrapolation capabilities with respect to this this hyperparameter ADA as well. That means you can actually train this ADA within a certain range, and without retraining, you can directly generalize to ADA that is generated, outside the range of the training. Okay, because of time, I'm not gonna bore you with more experimental details. You can find more examples in our paper. Okay, now let me move on to the to another interesting problem that I worked with Huawei very closely for the past a year. Well, this is one of their one of the problems that they're it's very important for them. That is magnetic simulations. When you design electronic devices, cell phones, for example, or chips, or electric vehicles, you want to do electromagnetic simulations for many times. For example, when you have a certain design of a cell phone, you need to conduct electromagnetic simulations for thousands of times, and that could be very time consuming. So the conventional way of doing it is to first do meshing. Okay, given a certain design, the geometry, the CAD geometry of your cell phone, for example, and you do meshing, and then you rely on commercial solvers. For example, for CST solver, they use the finite difference approximations to the solutions, or you can use finite element. And after that, you have your solutions, and then they extract a certain quantities based on solutions. For example, the scattering parameters. It represents the absorption or reflections of signals. And then the designers will look at this scattering parameters and decide whether this design is good enough or need further adjustment. And then they adjust it a little bit, and then they repeat this process. Maybe locally, I find this meshing to save some time, but most likely, mostly they just rely on this black box. They use this software as a black box. They generate a solution and look at the scattering parameters, to see if it's good enough. Okay, so you need to repeat this many times. So when we first started this project, we decided to take two different routes. The first route is that we want to speed up the numerical solvers of Maxwell equations. Okay, so this is the first route that you can take, and we want to use machine learning to speed this up. The second route is more challenging, but could be more beneficial. Is that we trying to establish a direct mapping from the CAD geometry to the scattering parameter, or to the whatever physical quantities that are interested in for a given task. Okay, so then if you establish such black box, well, the utility will be very limited, but it could significantly speed up this process compared to the first approach. So both approach has its own pros and cons. So actually we decided to investigate both approaches at the same time. So for the first approach, again, we want to solve a parametric PDEs, and this time the parameter that for the differential equations would include the domains as well, because when you alter the designs, you actually alter the boundary, the shapes of the boundaries. Okay, so this ADA for this type of parametric PDE, this ADA belongs to a space A, where this A is the space, it could be infinite dimensional space as well. Okay, and instead of thinking it as a multitask learning, we actually attempt on solving this problem by thinking it as a manifold learning approach. Well, this is not surprising because for the POD people, when people think of solution manifold of parametric PDEs and using PODs, which is essentially PCAs to approximate solution manifold, this is a very commonly adopted perspective. It's just when your solution manifold are highly nonlinear, effectively approximating a nonlinear structure is very challenging. But now we have deep neural networks. They are quite effective in approximating high-dimensional nonlinear objects. So there's a hope that we can do this better than what we did in the past. Okay, so no surprising of taking manifold perspective, but this is very helpful to help us understand this problem and help us to design a network, a model to approximate the solution manifold. Okay, so first of all, the solution manifold is actually a set that we denoted as a G of A, where this ADA goes through all of the all the possible parameters, which could be an infinite dimensional space as well. And this U eta goes through this, all the the solution space U, okay, which is function space. And this GA could be an infinite dimensional nonlinear manifold. Okay, we want to find, well, of course, we cannot use an infinite dimensional model to approximate it because we cannot compute it. So we need to use a finite dimensional ansatz to approximate this G space. Okay, so we call it G theta, where it's actually generated by a function f of theta, which is neural network. Theta is the network parameters, and it has input of the spatial variable x, and also a code z, which belongs to a certain finite dimensional latent space. Okay, so basically this is a decoder model. Okay, but it's a nonlinear decoder model, and this theta is the parameters of this decoding model, and it takes the input of x and z at the same time. So here we adopt an assumption where this G theta is indeed a, this capital G theta is approximatable by this G theta. Okay, this G it can be approximated using G theta in this fashion. Well, for very simple differential equation, for example, for elliptic equations, and if you're using linear approximation or sometimes using nonlinear, a nonlinear approximation of the solution manifold, you will be able to prove that there is a good approximation. And this is actually a very active research field. This is called metric, I think it's called the metric geometry, where people trying to prove, of course, approximation theory, establish approximation properties of solution manifolds for PDEs. But right now the theory is still very limited. It mostly works on elliptic or parabolic equations, and right now the results are very, very limited for hyperbolic systems. I think it's very, very challenging. So right now we treat it as an assumption, but for some simple cases, this is not assumption. This can be proved that it can be done. There exists a parameter theta that this can be done. Okay. So in order to achieve such approximation, we adopt this two-stage approaches. The first stage is a pre-training stage. This is the manifold learning stage, where we sample a set of zi, and also we sample a set of eta from this space A. Okay, and then we try to approximate this G theta to this G. Okay, that is to adjusting theta, which amount to say that we adjust the shape of the manifold to approximate solution manifold, and the training of this Z is to find the coordinates of the specific solution U eta, on this solution manifold F theta. Okay, so trying to find the correspondence of this U eta on the on this approximated solution manifold. Okay, so that's why you have this two object to optimize. Theta controls the general shape, and zeta determines the coordinates on the approximated manifold that associate to this parameter eta I. Okay. In the fine-tuning stage, you can treat it as a lifelong learning stage where you just train a little bit. We don't have to train. This n doesn't have to be huge. Okay. But this applications of the fine-tuning stage could be lifelong, right? You could have a new task coming in, and each time you have a new task, you need to adjust the shape of your manifold, okay, and also adjust the coordinates of z corresponding to this to this eta, so that you will be able to find that specific solution, and you do this at the same time. Okay, and this is actually very important, and this actually makes this approach different from an earlier work known as the deep SDF. They also use this autodecoder framework to learn a sign distance function, but they don't have this this manifold learning perspective, and in the fine tuning they don't actually fine tune this data. They don't have this lifelong learning perspective, and also they use a supervised learning approach. But here we use because we're solving PDEs, we use this physics informed laws, which is just the least square laws of the differential equations, and this is a specific network architecture. And there's another advantage of training your network in this specific way. That is, if your ADA that contains very heterogeneous objects. For example, if your ADA is both the shape of your domain and also contains the function, on the boundary, okay, the boundary condition on the, on the domain, then you don't have to worry, how do you actually encode the shape and encode the function living on the shape in a way that they can be, in an equal way that they can be incorporated into the network. If you do it this way, then this latent code Z, naturally handles heterogeneous, components that could reside in your ADA. Okay, let me show you one example in a minute. Well, this is just one example showing that if your solution manifold is actually finite dimension and you can actually approximate it precisely. Okay, if your solution manifold is one dimension and with this hyperparameter ADA, then during training of this data will actually get you closer and closer to the general shape of this solution manifold, and training of Z will actually converges for each Z will converge to the actual ADA. Okay, and during the fine tuning, when you fine tune theta, well, you adjust your manifold in general, the general shape of the manifold, and also when you're fine tuning this Z, it actually gets closer and closer to the actual Z that's supposed to correspond to the ADA. For this simple case, the Z is supposed to be equals to ADA. So this is just a proof of concept that for a simple case, well, this MAD, we call it meta autodecoder, does what we actually designed it for. Okay, so this is an example that I mentioned that when you solve a parametric PDEs where this ADA contains the shape and also the function defined on the boundary at the same time. So here, we assume that this shape is relatively simple, but you can do a more complex training as well. Okay, so they're actually random triangles. So we just randomly generate points, on the circle and generate triangle domains. Okay, and then we can during the inference we generate new triangle domains, and we can actually generalize to rectangular domains. And I we believe this is our future work. We want to do more substantial experiments as well, that we train on relatively simple domains and we generalize on more complex domains. Okay, but the point is to show you that if you have domains and also have the boundary functions, you can actually encode very conveniently this object at the same all together, and because of this can be viewed as a multitask learning. We also compare the MAD, the proposed method MAD, with mammal and also with the reptile meta learning approaches, and this shows that we have an advantage over these meta learning approaches, and also, well, of course it's significantly faster than training from scratch. Okay, so this is one simple example, and this is an example that Huawei are actually interested in. This is a very typical scenario, and where we're solving a 2D Maxwell equation with with a singular source, with a point source that actually that oscillates. Then comparing with other methods, actually the difference is actually more significant than the simple example that you see in the past. And if you wanted about 10% relative accuracy, okay, this is the accuracy 5 to 10% is more or less enough, for them to do designs later, okay. And we have about 20 times speed outs over PIDs, over training from scratch. So in this way, we find a relatively good balance between, like I said at the beginning, where we want to find a relatively good balance between not wanting to create a mesh, because this is still mesh-free approximation, okay, and this is also approximated solution mapping where we have a relatively light fine-tuning stage. This is not as fast as just doing inference. You still need to do a relative light training, okay, but you don't have to do mesh. So this is a unsupervised and also mesh-free version. So it's a combination between the two general approaches that I reviewed. Okay, so I only have one page to show you the other alternatives, that is to try to establish a direct mapping between the CAD designs to the scatter parameters. you can easily achieve a significant speed ups, even though it looks like this speed up is not as as much as here, but this is speed ups over pins. This is still slower than using CST algorithms. So this is still ongoing work. We're trying to actually making this fine-tuning stage more efficient so that we can actually beat CST algorithms. But this is not this is still ongoing. And here you can have a significant have a one magnitude of speed ups over the commercial software. Okay. But we're actually facing a very severe overfitting problem because we don't have, we need to narrow down the task to make it really task specific and to collect appropriate data and also to building, to building knowledges, to building into this architecture design. But right now, the network is more like a black box network. So again, this is ongoing work, but this is just showing you that the potential of trying to establish a task-specific direct mapping, versus trying to speed up numerical PDE solvers. So before I move on to the conclusion, I just want to let you guys aware of a platform. This is a platform developed by Huawei, and this is entirely free, and their codes are on this Giti, which is a Chinese version of GitHub. And MindSpore is a platform similar to PyTorch and TensorFlow. So if you want to explore a new platform and trying to to take advantage of the new platform, and also there are some problems with this platform, and I actually welcome you to try this platform and try to build your code and using this platform build your code, try to establish packages with this platform, and so that we'll have a good alternative to TensorFlow, PyTorch, or maybe JAX, and all those alternatives as well. Okay, so let me conclude. So we can view deep learning approximately as optimal control. And with that, this actually grants a very good framework to combine learning and handcraft modeling. Okay, so the way of doing that is, so for a given task, you start with the favorite dynamics like multigrid that I explained earlier, and you identify the component that is hard to handcraft. For example, to making the smoother that is adaptive to the hyperparameters in your PDEs, and you replace it by a properly designed deep neural networks. You pick a loss function, a properly designed loss function, and you pick a training algorithm. But because of the mechanism of training of deep learning is still mysterious. So, well, you should hope for the best, but prepare for the worst. So there are a lot of tuning and a lot of trial and error in here. Okay, but overall, I think this end-to-end perspective is really, really helpful, right? Either you rely on this this optimal control perspective and trying to build machine learning inside the collective solver, or you rely entirely on a relatively black box design, okay, or gray box design. I think this end-to-end is really significant in terms of speeding up for a given specific task, because you don't need, sometimes you just don't need very high accuracy. You just need about right accuracy for a specific given task. But to do that properly, you obviously need data, but sometimes it's more important to incorporate the domain knowledge that you have the problem in hand. Okay, with that, I conclude my talk, and thanks for your attention.